So how do we choose an experimental design that's both practical and can also be analysed with some of the statistical approaches we've learned in this unit? The specifics are, of course, going to depend heavily on the system that you're working in. But here I'm going to tell you about some of the practicalities I've encountered in my own laboratory research, which will hopefully give you a place to start from when designing experiments in your own systems. So my current research is nothing to do with fish. I'm interested instead in understanding how antibiotic resistance evolves in bacteria. And this involves a lot of performing laboratory experiments to understand how resistance evolves in the presence of an antibiotic treatment. And one experiment I've done since coming to Manchester was to look at the rate of resistance evolution for several different antibiotics. A simple question I started with was, does resistance evolve at different rates for these 3 antibiotics? So I did an experiment where I grew E. coli in the presence of these antibiotics for 35 days using a standard culture vessel. If you're used to doing microbiological or tissue culture experiments, you might have encountered a 96 well microtiter plate. It's a very standard piece of equipment. And now I'm studying evolution. So I wanted to have a really large amount of replication because evolution being a random process, to understand how things happen in a repeatable way, you need to have lots of repeated examples of the process you're studying. So let's look at some possible designs. I have 3 antibiotics, and the most obvious design might therefore be to put each antibiotic on a separate 96 well plate. Now, this is problematic because this would confound the variation in the evolutionary rate that's due to the different antibiotics, potentially with any error or noise we don't care about, which is introduced by having experiments running on different physical pieces of plastic. In this approach, we can't estimate a block effect, and therefore this design is not very effective. We really actually can't say whether any difference in evolutionary rate is down to different antibiotics or down to being on a different plate. So this design is not good. The second design would be to randomize each position on the 96 well plate with a different antibiotic or with the antibiotic-free control. Sorry, I forgot to mention. This is a perfectly reasonable design from an analysis point of view, because by randomizing the position of the antibiotics and the control, we partition any noise introduced by the spatial aspect equally across all the different antibiotic treatments. Now, a third design we could employ is an incomplete block design, where instead of randomizing the positions of the antibiotic, instead we place them regularly but distribute them across a plate. In this example, each column here contains 2 of the 4 treatments, and each row contains a different set of 2 of the 4 treatments. The position of the antibiotics, as I said, isn't randomized, but the effect of distributing the antibiotics evenly also seeks to distribute that noise across the different treatments. Thinking back now first to our completely randomized design, from a statistical viewpoint, this design might be the most straightforward to fit a model to. You could you could fit block effects here, accounting for whether an antibiotic appeared in one of the 8 different rows or the 12 different columns, and another block effect for plate. In this case, we have 3 different plates, just as an example. But actually, since the antibiotics are randomly assigned, the extra variation for each block would naturally be apportioned to each antibiotic. So in fact, it wouldn't be strictly correct, but you could probably get away without fitting any block effects at all and still come up with the same qualitative result. Now, it's important to consider that all of this design might be easy to analyze. Practically speaking, filling one of these plates means that you take a pipette and you have to fill each well by hand with a liquid that's clear. Here in this example, they appear to be colored, but actually in practice, the antibiotics are not necessarily colored. Now, considering that we have 3 microtiter plates, each with 96 wells, and an experiment that is going to run over multiple weeks, 35 days in total in this case, this would require doing more than 10,000 pipetting operations correctly without making a single mistake. I've been doing this a long time. That's very unlikely. I think people make mistakes all the time, and if you can take any chances to minimize the possibility of making a mistake, you should do so. 10,000, not gonna happen. If we were to try this and we did make a mistake by putting the wrong antibiotic in the wrong well, this is going to introduce extra noise into our experiment. And what's more critical even is that when that mistake happens, we're not going to know about it because I said the antibiotics are clear and this is going to introduce noise and we're not going to know why. So this is not necessarily an ideal design, practically speaking, although it might be the most easy design to analyze statistically speaking. So if this completely randomized design is problematic, what can we do? What can we do to get around this problem? We might instead look at this incomplete block design, where now the placement of the antibiotic is regularized, but we still have some control of positional effects because the antibiotics are still distributed across each plate. So with this incomplete block design, as I said before, each row and each column contains 2 of the 4 antibiotics. So we can estimate a block effect, unlike when we had different antibiotics on different plates, across both the rows, the columns, and the plates here. If we wanted to make things simpler, we might even be able to consider this as rather than an incomplete block design, as a complete block design. If we took each cluster of 4 wells, so if you look at the top left corner, the 4 wells contains each of the 4 different antibiotic treatments. We could treat these as a block, and then we could analyze it as a complete block design. So it just really depends which statistical approach gives you more power at the time of analysis. Now, if I had to fill this 1 well at a time, I would still have about 10,000 pipetting operations to do perfectly. But since the pattern of where the antibiotics appears is more regularized, the chances I'm going to make a mistake are much less. However, I might also be able to use other tools I have in the lab that allow me to fill multiple wells at a time, thus filling the plate faster and therefore potentially increasing the amount of replicates I can do, which if we think back to the first slide when I set up the experimental requirements, having high replication was one of the stated desires. And so if I can, instead of using the single channel pipette where I fill 1 well at a time, I can use a 12 channel pipette where I can fill 12 channels at a time instead. And this potentially cuts my 10,000 pipetting operations down to just 840, which is a much smaller chance of making a mistake. And also quicker and better from a repetitive strain injury point of view. So that's also very important to consider. Now, it turns out I can even do better than this incomplete block design because I have experience working with this system. And my prior knowledge about how this bit of kit works, this plasticware works, is that the wells on the outside of the plate tend to evaporate faster than the inside wells due to just the effect of being closer to air and less insulated. So I know that if I use these wells, I might introduce extra noise into my experiment because the bacteria could be stressed out due to the increased evaporation. They might even start to adapt to this increased evaporation effect. And I don't want that. I'm not interested in evaporation. I'm interested in antibiotics. And so what I might do instead is fill those empty wells without any bacteria, those outside wells without any bacteria, leaving them empty in effect. And although this means I now have less replication, I lose 36 out of the 96 wells from each plate. The reduction in noise might make this worthwhile. And I know to consider these edge effects in this system because I've been working with these plates for a long time, just over 10 years now. If you're new, you might not have the same background experience, but if you talk through your experimental design with your colleagues, with your lab mates, you might be able to benefit from their prior knowledge as well.